I'm going to explain about enhancement mode transistor action. Enhancement mode means there is no channel between source and drain while fabricating a transistor. Means some extra power, extra supply is required to form the channel from source to drain. So we can see this. So I have taken either P substrate or N substrate we can take. So this is the metal. We are diffusing electrons to design source and drain terminal. But here there is no channel from source to drain. From here to here, there is no channel from source to drain while fabricating a transistor. Source, gate, drain. So I will explain clearly. There are three regions in enhancement mode transistor action. So here there is no channel from source to drain. Some extra supply is required to form the channel from source to drain. Then only it will goes to, that is, active region or saturation region. So extra supply is required for enhancement mode transistor. So, and it is having three regions. I will explain clearly. One is cutoff region, just assume cutoff region, and ohmic region, and or resistive region, ohmic or resistive region, and saturation region. So I will explain clearly what is the enhancement mode transistor action. So here you can see this, these are the three regions. So this is the first case and second case. I will explain clearly. Here you can see this is the third case. So here you can see this, the first case. I am assuming that is first case. Enhancement mode means, as you know, that there is no channel from source to drain. So in this case, it is having polysilicon material. To design gate terminal, we have deposited polysilicon material, that is named as gate, and we are diffused. This is P substrate having holes, and if you want design source and drain terminal, diffuse the electrons here. So this is the electrons and this is the electrons here. So these are the electrons. So this is named as source and this is named as drain terminal. So there are three conditions. One is when VGS V is greater than V threshold, and there is no VDS, you are not applying VDS, is 0. So you can see this is the voltage between source and drain, gate and source, is called as VGS. Here you can see this VGS, and VDS means from here to here. VDS, voltage between drain and source. This is the voltage between drain and source. So here just assume that the threshold voltage for the transistor, I am assuming 0.6 volts. So it is 0.6, but we are applied only, that is 0.2 VGS, just assumption. So in this case the condition will not satisfied. You can see this VGS is less than or equal to threshold voltage, means the transistor will not goes to active because still it is in cutoff region only. So you can see this. You can see this. This is the symbol you can see. Source and gate and drain. Source, gate, drain. So this VGS is greater than VT. So means we have given only 0.2 volts, but the threshold is 0.6. So means here the depletion region will not decrease. So means there is no channel is formed from source to drain. So means here it is in cutoff region. There is no current flow from, that is, source to drain in this case clearly. So because the minimum threshold is required to break this threshold. So this is the first case, first condition. So of course here these are the holes. So this is called as cutoff region. And coming to the second case, you can see this. You can see this here. So same thing. The transistor is having either P substrate or N substrate. I am taking P substrate and to design gate terminal, deposit the polysilicon material. This is the polysilicon material. And to design source and drain terminal, diffuse the electrons into P substrate by hitting this material. So this is an electrons. So second case I am taking, of course this is named as source and gate and drain terminal. So second case, there is a sufficient VGS, voltage between gate and source, VT. So means I am assuming this is 1 volt is greater than, that is 0.6 volts threshold. Threshold voltage for the transistor is, that is 0.6. So means there is a sufficient VGS, first condition. And second condition, VDS should be greater actually, but it is less, just assume VGS. Of course, the threshold voltage need to remove because of net voltage, that is minus VT. So means here you can see this VGS from source to gate. As I said, this is an VDS, voltage between drain and source. Voltage between drain and source. But it is less. VGS is greater, but VDS is less than or equal to VGS. So that is the reason here there is a channel is formed from source to drain because of sufficient VGS, but current will not flow from here to here because of insufficient VDS. So VDS is not sufficient, so but it will goes to, that is the reason it is named as, that is ohmic region, or else that is resistive region. Ohmic or resistive. You can say this because of sufficient VGS, it is, the transistor is inactive. Channel is formed. There is a chance to flow the current. So, but there is no flow because of insufficient VDS. When the current will flow sufficiently, when VDS is greater. When VDS is greater, so the current will flow. So this is the second case, and VDS less than or equal VGS minus VT. Because of insufficient VDS, the current will not flow. This region is called, that is ohmic or resistive. Coming to the third case, and this is, and one more thing here, we can say this depletion will start to decrease. This depletion will start to decrease because of sufficient VGS. So that's why in the diagrams you can see, you can observe this. Some of the textbooks are having like this. Slowly it will start to, this depletion will start to decrease. So that is also named as pinch off region. And coming to the third case, last case, when VGS, you can see this is an P substrate. Again, we are taking having holes to design gate terminal, deposit the polysilicon material, and to design source and drain terminal, diffuse the electrons into P substrate. So this is N. Now it is named as source. Of course, here metal is there, and it is named as gate, and it is named as drain terminal. Now the first condition is satisfied, that is VGS greater than should be equal to VT, threshold voltage. To break the junction, the threshold is required, that is just assume it is 1 volt VGS, and of course for silicon material it is 0.6 volts per transistor. Just assumption, threshold voltage. And VDS, now we can say this VDS should be high here, just in the case, this case, and compared to VGS. Of course, net voltage is minus VT. We can say this voltage between drain and source is greater here, is greater than VGS, than VGS. You can say this. This is, assume that this is VDS, voltage between drain and source, source, gate and drain. So this voltage between drain and source is greater than voltage between gate and source. Just assume that. In this case, just you can say this, this is high voltage. Sufficient voltage is there to flow from, that is forward bias, just like it is like a forward bias. So in this case, the junction will break down from source to drain, and here the channel is already established from source to drain, and of course the depletion region completely break. So and current will flow constantly. That is the reason this region is named as saturation region. Saturation. Why? Because you can say this, VGS is sufficient and VDS is sufficient. Both are sufficient. So that is the reason this is named as, that is saturation region. And in the second case, it will goes to just active because of insufficient VDS. The current will not flow maximum. So but the channel is formed between source and drain. In the first case, it will not go because we are not applying any VDS. So and channel is also not there because of insufficient, both are not sufficient. VGS not sufficient and VDS is also not sufficient. So these are the three regions for NMOS enhancement mode transistor action. So if you go for PMOS, so here we'll get just N and here you can get P. So now it is N diffusion here, NPN. If it is PMOS enhancement, we'll get opposite, that is NPNP transistor. Thank you.